So this video is going to introduce the PLC fundamentals and the Heatbox. So first, let's just look at a brief history of PLCs. Before PLCs, there was what they called the relay era, which consisted of just thousands of hardwired relays and timers and counters. And so this made it very difficult to troubleshoot. They were mechanical devices, so they would fail a lot, and it was just quite complicated and stuff. I mean, they worked, but it was just kind of very troublesome to solve when things failed. So in 1968, we had the birth of the PLC. So there was an engineer by the name of Dick Morley, and he later created the company called Modicon, or the PLC called Modicon, which is still in business. And they first installed it at GM Motors. So it was installed at the Hydra-Matic plant in Minnesota. And it was able to, just one PLC was able to replace a full room of relay panels. And the way they set it up was they used ladder logic, which was pretty much a one-for-one for relay logic. So they could just take the relay program that was there, transfer it into this ladder logic, and be able to greatly simplify it. So these became very popular, and Allen-Bardley entered the scene in the 70s with what they called the PLC Model 2, and then the PLC Model 3, and eventually they went up to the 5, and then 500 and 5000. Alright, so in the 80s, with the microprocessor revolution, they were starting to get much smaller, much faster. And we could use PCs to actually program them. Before the PC, they had to have specialized programmers, which were much more cumbersome. And then they started, of course, adding networking in there. And so in the 90s, we began integration and what they call openness. What they're calling openness here basically means like more friendly to third parties to create devices that or cards for the PLC. And then today, of course, we have dedicated safety PLCs. Allen-Bardley calls theirs guard logic, and we also have the combination, which we saw in the previous lab, where we can actually interface the PLC with other edge computing devices. We use the BeagleBone to do Ethernet communications. So let's look at the PLC operation. So there's a scan cycle, and the idea of the scan cycle is that you're going to read the inputs, you're going to process the program, determine what the outputs are going to be, and then do what they call some housekeeping kind of system sort of stuff that has to be done, and then you send your outputs. So this is what we call a loop or a scan. So every so often this will happen. Now the timing for this loop or this scan depends on a couple of things. Number one, it depends on how fast your PLC is. Number two, it depends on how long and complicated your program is. So those are the two main things that dictate how long the program is actually going to take to run through a single scan, and where it collects the new data, the new input values, does its processing, and then sends output instructions to the devices. So as I was saying here, the input scan is just going to read all the inputs, and then those values will remain that value for that entire scan. So the scan may take 1 millisecond, maybe it'll take 10 or 20 milliseconds. But for that time, as far as the program itself is concerned, no inputs are changing. Now they may change dozens of times during that scan, but as far as the PLC, inside the PLC and inside the program, it's holding those values constant. So it runs like ladder logic, goes down the ladder, so it runs from top to bottom, left to right, and it evaluates conditions and then updates the internal memory. And then once the internal memory is done and it does its internal system kind of stuff that it also has to do, then it sends those outputs. And then it reads the inputs and starts all over again. So I already kind of mentioned this. Scan time can vary depending on the length and length of the program and the speed of the PLC. Also, when you're monitoring it, so when you're connected with this RSLogix 5000 or Studio 5000 software, depending on which one you're using, that will kind of slow down the program because it's sending the data back up to the PC so we can see it. All right, so lots of different applications for PLCs, conveyor systems, robotic cells, packaging machines, just any sort of moving equipment that you want to control, basically. So this couple of slides are just kind of talking about where we can use these. Okay, so why do we want to use a PLC? Well, we kind of talked about a little bit of this back in the controller lecture. We talked about the different types of controllers and stuff, and what the PLCs are designed for are high reliability in harsh manufacturing type environments. So they're also very easy to program and maintain, and they give us real-time deterministic control. So this is something like an ordinary PC, even though it may be 100 or 1,000 times faster, it doesn't guarantee us that the things are going to be done in a very deterministic real-time manner, but the PLCs do. So for us, we're going to be using the Allen-Bardley ControlLogix 5000's series PLCs. And these PLCs are really nice. They're like I say, they're the flagship basically for Rockwell Automation. They are modular, meaning that you can pull in or you can select different I/O cards that you need, and you expand them. They're very expandable. They do network communications. And the older versions, which is what we actually still have in the lab, are running on the RSLogix 5000, which the newer version of the software is Studio 5000. However, it depends on the firmware of the PLC. So the PLCs have what they call a firmware, and that firmware tells you basically whether you're going to use RSLogix 5000 or Studio 5000. So some of the key features we can do multi-processor support, so we can actually put multiple processors in the chassis of the ControlLogix, where most of the other, at least Allen-Bardley PLCs, you have one processor that has to do the work. But if you have to do a lot of processing with the ControlLogix, we can actually insert multiple processors so they can be doing different things. Okay, they have native Ethernet industrial protocol communication built into them, as we kind of saw in the previous lab, where we were able to send things across. I think we were using the CompactLogix then, but again, built-in Ethernet communication for networked I/O and high-speed backplane or chassis. So the chassis is called 1756. So anytime you see 1756 at the beginning of a model number for Allen-Bardley, that's telling you It's a card that will fit into this chassis, and therefore you can use it with your ControlLogix PLC. All right, we can actually do many different types of programming languages with it. We can do what's called the ladder logic, which we're going to look at here, and then the function block diagrams, or something called structured text or sequential function charts. Okay. And we already mentioned the safety ones are referred to as GuardLogix, and so they have extra features specifically for security. All right, so now let's look at the data types and or tags for the Allen-Bardley PLCs. So we have basically about 6 primary data types here. We have the Boolean, which is a single bit, a 1 or a 0. We have a int, a single int, which is actually only 8 bits. That's not very used very often at all. And then we have the integer, which is a 16-bit integer, which can go from minus 32,000 to plus 32,000. So those are the range of numbers that you can store in 16 bits, where one of the bits is the sign bit. And then they have a double int, which is a 32-bit. This is what's common for like your count values and timers and counters, or if you're converting data into analog data into digital data, it comes in as like a count, and that would be an integer. And then they have real bits. Now the real are real tags. Real tags are just stored in the PLC, so they can't be coming directly in. You'd have to like bring it in and convert it into and store it in a real tag. And then you can also do string data. Now a tag is Allen-Bradley's term for a variable. So in math class, they like to say, oh, well, we have a variable X and a variable Y and a variable Z. Allen-Bradley uses the term tag instead of variables. So the older PLCs, you would have to like define, okay, I have a number, so that would be an integer, and it was in block 7, and then you'd have to specify the bit, and it was just very obscure and harder to work with. So now we can actually give these numbers a more meaningful name, as we'll see here with some examples. All right, so we have our tag. You can have either a virtual tag, which means it only is stored inside the memory, inside the PLC. Or you can have a tag that is a map to the physical wiring out to a switch or a light or a analog card, an analog input, analog output, or whatnot. So if you see here, I have a little screenshot here from the program here. We have a tag, which is a stop bit for the stop switch. So this is a physical stop button wired into the PLC. And so its actual physical wired location is the alias. So the alias tells us, well, this is actually wired to a local card. So you can have either local or remote. Okay, so local means it's inside your current chassis. Remote means you're accessing it across the network. And then the card number. So you see the 4 is the card number, or the slot number. Now the slots start counting at 0. So this is actually the 5th card in the chassis. And then I stands for input. And then data.0 means 1 bit. So this is 1 bit, which is type Boolean or bit. And then you also have the scope. So you can actually have multiple programs. You can have what they normally call the main program, and then you could create other programs which would most likely be sub-programs to the main program. And so you can have scope of where these tags are accessible by, for what programs can access it. This next tag that I have here is a virtual tag. This is a temperature reading. So it's reading the actual temperature. So this value here is 83.1 with some numbers here. So this is a real value because it has a decimal point, but it's only stored inside of the PLC. Where the stop bit here had a value of 1. Meaning that it was true, or it could be a 0, and that was its only choice because it was Boolean. But this is a real value, and the reading here was the reading that it was when I captured this data. And then we have an integer value. So this is an integer. Its current value is 2381. It is coming from a local card, which is in the slot 2, which again technically is the third slot in the device, counts from 0, and then I for input, and then this is channel 4 data. So see, this is a 16-bit integer. This is the analog input card. So we're looking at channel 4 input, and so what it's doing is it's reading a voltage, a physical voltage, from a temperature sensor, and then that is getting converted into a binary value, which I like to call a count. And so the current count is 2,381 is the current count. Now that then, using a compute statement, was converted into an actual temperature, which here is 83.1. This would actually be degrees Fahrenheit. So when I did this conversion, I was converting it into degrees Fahrenheit. So this count is what came into the PLC, and then we have to scale that into your temperature. So as I already mentioned, we can have virtual tags. Virtual tags means that they only exist inside of the PLC. We also have what's called produced tags. So if it's a produced tag, what that means is that this PLC is producing that. It's either computing it or it's pulling it in from an input sensor or input value. And then it's going to broadcast that over to other PLCs if you're using like the Ethernet IP or some other network where you're sending it across the network. Where consumed means that you're receiving a tag from another PLC and then you're going to use it in your program, but it was generated or from another device. Could be a robot or another PLC or just a remote sensor. All right, so I wanted to just kind of list some information about these I/O cards. You can find this in the manuals, but I thought it'd be handy to have it here in the slides. So if we have, here is the 1756 OB16 card. I believe this is the one we have in our PLCs, but I'm not 100% sure. But the O, notice the O means output. The 16 means 16 data points. Okay, and this particular card here is a 24 volt card. So it's 24 volts DC. It's an output card, so we're outputting that, and it can actually output up to 2 amperes for each point. And so I was pretty impressed with that. Didn't realize that they had that much ability to send current out of those cards. Another card that we have in our PLCs is the output relay card. So this is a relay card, which means that what you have to do is you choose what voltage the load is going to have, and you would have to then wire that into a point on the card, and then usually it can then, that same voltage will drive at least 4 or maybe 8 points on your card. Now this is an OW16 card, which means it actually has 16 relays, but again, you can wire in the voltage into that. I think I didn't put that here on the card. I think it can do either in blocks of 4 or blocks of 8. So you could send out, with this one card, you could have a couple of different voltages on that. And so for AC voltage, you can go anywhere from 5 to up to about 265 volts AC. DC, notice DC is almost always lower because it's harder to break the connection. And so these relays are only rated for 125 volts DC. But and they can handle about 2 amperes of current through them. The analog input cards, the ones that we have is the IF16, which means there's 16 channels, and they can either read in voltages from plus or minus 10 volts, or they can read in currents. So the difference is how you wire them up. So you'd have to look at the manual and figure out how to wire it up, whether you're doing current or voltage on there as far as the wiring. And they're 16-bit resolution, which is very high resolution, so they're very good cards. Our output card, the one that we have, is the OF6C. So this means that it has 6 outputs, and the C means that it only outputs current. So there's like this OF8 card up here. Depending on how you wire it, could either output a current or a voltage, but we don't have those. We have the OF6Cs and our PLCs, so they only have 6 channels. Well, they have 6 channels, but they only output current, so you can't output a voltage. And again, that current is going to be 4 to 20. Technically, it's 0 to 20. It'll output 0 to 20 milliamperes. All right, so let's look at some standard ladder logic here. So the first circuit is what we call a fill-in circuit, and this is what a latching or a holding circuit. So this requires a couple of contacts. And so if you look at the top rung here, this is a fill-in circuit where I have the stop switch, which is wired in as normally closed. That's why it's green, showing up green here is the contacts are closed. And then we have a start button. So to start it, you have to make sure that the stop button is not pressed because it's wired closed, so it's a 1 when it's not pressed. And then you press the start button. That gives you a 1 and a 1, which will then energize in this case the red light tag, which will turn on the red light. But then once the red light is on, you don't have to keep holding the start button because the red light is now on. So as long as you don't press the stop button, you have the stop and the red light. So the start and the red light here is what we call an OR path. So you can either go through the start or through the red light path and energize your red light. But the stop is ANDed with either the start or the red light here. So you have to stop, and so you're not pressing stop and you are pressing start, or you're not pressing stop and the red light is on. Alright, so let's talk a little bit about timers. So we have 3 different types of timers. We have a timer on, which means that it's going to count up until it's done. And then it'll be, we'll have a done bit that'll go on. We have a timer off, and then we have a retentive timer. So in this rung I have down here, I actually have a timer off. And so the way the timer offs work, they're a little backwards in my opinion, is but they're good for having things like keep running. Like say you shut off a system and you have a fan that cools it, and when you shut it off, it'll tend to get hotter because if the fan's not running. So the idea here in this case is to have this delay fan run so that it'll run for a certain amount of time. In this case, I said 30 seconds up here, but I changed that time to 200 milliseconds actually in this case. So the this move statement, which we'll technically talk about the move statements a little bit later here, but the move statement, what I did was I created a tag to set how long my timer is going to run, and then I move that into the pre-tag for the timer on here. Now the reason I did this was because you cannot change this preset value. If you just hard code it to 200 here, which I guess I did there, you cannot change it when it's running live, but you can change just a virtual tag. I could go in there and change this, and then the move will move my virtual tag into the pre value so that it would run. So timers have basically three variables. So the timer is a structure or an object that has multiple different tags within it. And so three of those tags are Boolean. That's the timer enabled. This tells you that the timer has been activated. Okay, now it depends on which kind of timer it is, whether that means it's actually timing. So timer timing means it's timing, and then timer done means that it counted up until it exhausted its time and then it stopped. And then we have two integer values. The one integer value is the accumulated time, telling us how much time has passed, and then the other one is the preset. So when the accumulated time reaches the preset, that's when the timer is done. Now notice for the ControlLogix 5000s, these are timers values are, again, they're they're double ints, so they're 32-bit integers, but the number you put in is in milliseconds. So if you want to time for 1 second, you'd have to put in 1000 milliseconds. So here is a timer on, and again, in this case, I'm using this preset, a move, to move the preset value to 200. The accumulator is at 22. So the now in this case, this timer is always on because there's no control over here to activate it. So it's always enabled. So the enable bit is green, telling us that that's a 1, but the done bit is not done because it's only at 22. It's got to get to 200, and then the done bit will turn on. Now in this type of thing, what I would have to do to restart the timer is I would have to use a reset rung later on to reset my timer. All right, so anytime you want to time something, obviously you would have your timers in there. We can also have a counter. Now the difference is basically timers are counters, but timers count time in milliseconds, where counters just count anytime we tell them we enable them and activate them, we can get them to count. We can count up or we can count down, and then of course you might need to reset your counter, which is identical to resetting the timer. So we have basically 5 bits here. We have a CU, which is a count up bit, which tells it that you want the counter to count up, and then we have a count down bit, and then we have the done bit. So the done bit is when it's reached the preset value. And then the accumulator is the current count. So when the accumulator, every time you activate it, meaning that the rung was false and then it goes to true, that is 1 count. and it'll advance the accumulator value by 1. And then when the accumulator is greater than or equal to the preset, it'll hit done. There's also an overflow bit, meaning that the accumulator has reached, so if you keep counting after it's done, then it'll also flag the overflow. All right, so here's an example of a move instruction. Actually, what I'm using here is a selector switch. So I have a 3-position selector switch. So on the left side, it turns, the selector switch is wired into bit 2 of the input card on 4. And so if the switch is turned all the way to the left, it'll activate this, which will move a value of 30 into a tag called set point. And if it's in the center, then neither the bit 2 or the bit 3 are a 1. They're both zeros, and so therefore it's moving 50 into the set point. So you see here set point is 50, 50, 50. That's because this middle rung is the one that's currently active, so meaning the selector switch is in the center position. All right, we also have compute instructions. Now you can, if you just need to multiply or add, they do have add or multiply or divide blocks, but that only does one calculation. If you will need to do more than a simple one calculation, then you need to use a compute statement. So in this case here, counting a flow. This was for a tank sensor and or a tank pump, and I'm counting how much data is flowing. So I have a flow count. So this is my analog input coming from card card 2, which is the 3rd slot. And then I have a scaling factor called my slope M, and then a intercept value. So this is my scaling factor, and this was the last calculation then done on this compute statement. All right, we can also do comparison blocks. Comparison blocks allow us allow us to compare tags and see. We can see if they're equal, if they're not equal, if they're less than, greater than, and so on. Now be aware, if you have a floating point value, a real value with a decimal point, you almost never want to try to do a equal or not equal, because of round off and stuff, these are not valid. You'll almost never have a case where they are 100% equal, just because of rounding. And so you definitely want to use things like a greater than or less than kind of thing for those. All right, but these allow us to set alarms or various conditions based on the control blocks. All right, so here's an example of a computation here where I have my actual temperature. So I've scaled my temperature, and it's at 83.1 degrees Fahrenheit. And if the temperature, which is A, so if the actual temperature is less than 0 degrees, then I'm saying that the fan is, that the system is too cold, and I'm going to turn off some fan or something over here. And then here I'm saying, well, wait a minute, if the temperature is greater than 115 degrees, then I want to turn the fan on. Okay, so I'm saying if the temperature, I got a temperature sensor reading, right now it's 81, so this is not going to be on. But if it gets at 115.0, so that means 115.01, this would turn on. All right, so in in the lab, we're going to use an RTD to read temperature. So I'm just going to talk a little bit about the RTD. So we have an RTD 385, which is a Platinum 100, which is a very common RTD sensor here. So this sensor is made out of platinum, and at 0 degrees Celsius, right, or freezing, at the point where water turns to ice, this RTD will have exactly 100 ohms of resistance. And then that resistance will change based on 385 ohms per ohm degree Celsius. Okay, so that's where the 385 in the name comes from. Now you can get these in 2, 3, or 4 wire devices. The ones we have in labs are 3-wire devices. Now, a couple of things about these RTDs, okay? They are very stable as long as you don't put too much current in them. So they're basically designed to work with 1 milliamp or less of current in them. But they can actually handle all the way up to 20 milliamps. All right, so to use an RTD, there's a couple of things you can do. Number one, you can buy a card specifically for RTDs. So if you're going to use multiple RTDs, if let's say you know, a lot of these cards can handle again, maybe 4, 6, or 8, maybe even 16 RTDs. So if you need a lot of RTDs, if you're using a bunch, then that would be the way to go. But if you're only going to be using maybe 2 or 3 or just 1, then what you could do is you could get a what they call a RTD transmitter. And so the idea here is you would wire in your RTD. This transmitter would put current through this RTD. Remember, the RTD is a resistor, so it needs to have current running through it. So what they're doing is they're going to run the current through this RTD and then measure the voltage. So this transmitter is driving a current through the RTD and then measuring the voltage across the resistance inside that RTD. And then it's going to convert that into a 4 to 20 milliamp current to send to the PLC. So that's what these transmitters do. Now they cost maybe $50 or $100 or something. They're not real expensive, but you know, they're an extra piece, and you're going to have to power this. So you're going to have to get 24 volts to this to actually power it. Where if you had a card plugged into the PLC, it's going to eliminate this transmitter piece out of the thing. You just have to wire the RTD right up to it. All right, so when it comes in, then you need to scale it. So again, when it's coming into the PLC through a transmitter, then it's coming in as a count. That count represents your current. So a count of 16,383, for instance, might mean 20 milliamps, which means that the RTD is pretty much maxed out at its limit, which or whatever. So you'd have to scale this. So these values here are example values. All right, and again, you would use a compute statement in there. Now, for us in class, we're going to use a 3-wire RTD, but we're only going to use 2 wires. Now, the RTD, again, would like to have 1 milliamp in it, but we don't have one of those transmitters. So what we're going to do is we're going to use our analog output card to drive 10 milliamps, but we don't want all 10 milliamps to go through the RTD. Technically we could do that, but I don't really want that much current running through the RTD. So what we're going to do is we're going to run it through a shunt. This is a parallel connection. So we have a 33 ohm shunt resistor and the RTD, which is 100 ohms at 0 degrees. So remember, this resistor in the box here, this is 100 ohms when the temperature is at 0 degrees Celsius or 32 Fahrenheit at freezing. And so what'll happen, 33 ohms, right, is about a third of that. So what we're going to get is about 2/3 of the current, a little more than 2/3 of the current is going to go through the shunt, and what's left over is going to go through the RTD. And so if you calculate that, I do that on the other slide here. I actually did these calculations for 80 degrees. Actually, I asked AI, I had Grok do this table for me and calculate this. But so the actual resistance from 80 to 120 degrees, you can see the estimated actual resistance of the RTD here. So the RTD would have about 2.4 milliamps running through it here. And then if we look at the counts inside the PLC, again, what we're doing here is we don't have a transmitter, so we're just going to read the voltage. So we're measuring the voltage drop across this RTD. And we know that if it's we can then measure the count, we can measure the temperature, look at the count, and then scale it into an actual temperature inside of our PLC. All right, so using this RTD, what we're going to do is we're going to measure the temperature inside of a box. So I have a little heat box, which is just got a couple of power resistors in there and some MOSFETs. And what we're going to do is we're going to just turn on the MOSFET. The first MOSFET is going to activate the current through these 25 ohm resistors and just heat it up, right? Resistors turn current into heat. And then we also have a fan powered by another MOSFET. And so the idea is we want to get the temperature in there and keep it at about, say, 100 degrees Fahrenheit within the box. And if it starts getting above that, then we'll kick on the fan and drive some air through it to cool it off. All right, so we're going to use this MOSFET here. Here's the part number. I'm not even going to read that there, but here's the wiring for the MOSFET. Now, this is actually already pre-wired for you on the box, and then the box is marked. We only have to worry about basically powering the gate and getting 24 volts to our resistors and to our things, and just power the gates to turn these on and off. We also actually have some temperature sensors already inside of this that we could also wire up and monitor those. Okay, so here's some sample tags. I'm gonna, in the lab, I'll specify names of tags that we can use in there, but this is just a sample program that Grok came up with for the ladder logic to move in the raw data, the analog value coming in, and compute it into degrees Fahrenheit. And then based on that, using a less than box to turn the heater on, or a greater than box to turn the fan on. And also they threw in a over temperature alarm if it gets too hot. All right, and what we could do is we could get into what they call PID control, which is proportional, integral, and derivative control. And we talk about that in the PLC 2 class, so some of you may have already done that in there. So, but all right, so anyhow, so we kind of looked at a little bit of history of the PLCs, and then some details of the ControlLogix, and talked about the Heatbox for lab. So that's the end of this video.